Hi everyone, this is Team Band Play AI. This is our brief demonstration on the Azul project for our subject AI Planning for Autonomy. I'll introduce three techniques, the challenges we faced, and some possible improvements. In the Azul game, certain tiles would be randomly drawn from the back to the factories, and players need to pick tiles from the factory or the center of table to fill the wall based on some rules. The game ends after the round in which at least one player has completed a horizontal line of 5 consecutive tiles on her wall. An object is to get the most points at the end of the game. So how to pick tiles and fill the wall are very important. And we applied some search algorithms to help the agent to make wise decisions. The first one is greedy best first search, which is based on the heuristic search. It will always take the action leading to the next stage with the lowest remaining cost to the goal. Here we use relaxation techniques to construct the heuristic function. At first, we place the tile from the pattern line on the grid wall immediately without filling the pattern line. And the second is to calculate the estimated score immediately before the round ends. The method is simple and easy to implement, and is suitable to be used as a functional module in other advanced techniques. However, it's neither optimal nor complete, and its performance relies on the quality of heuristic function. The second technique is min-max algorithm with alpha-beta pruning. We assume each round is a sub-problem with a constructed game tree. We set a threshold to limit the tree depth, and we use alpha-beta pruning to reduce the branch factor by cutting some obviously non-optimal branches. This method simplifies the problem and reduces the computation. However, it still needs a considerable number of searches as the complexity increases exponentially with the number of layers. And another method to reduce the branch factor is sampling simulation. In Monte Carlo tree search, expected max search tree is built incrementally based on simulation and backpropagation techniques. To improve the efficiency, we combine the MCTS and upper confidence bounds policy to balance exploration and exploitation so as to decide the next node to expand. It has the strength to reduce searching time significantly, since time limitation in this game is 1 second for each move. When we developed this game, we also encountered some challenges. At the beginning, when we implemented naive UTC agent, it performed like a random player and always get very low points when playing with the naive player. So we decided to simulate at a ground level rather than the game level and use round score instead of final score to estimate the rewards. However, it still did poor at the beginning of each round, especially the first round. So we managed to derive a competitive starting rule. One method is to replace the random rollout policy with naive policy. Another is to apply heuristic value or rule-based policy before using UCT. And at the end of this project, we also consider some possible improvements we would do if we had more time. We may try to improve the value estimation function and find a better rollout policy to improve simulation performance. And we were also willing to try to combine it with the deep neural network, such as deep Q learning. Thanks for watching.